questions I left at the end but didn't do is this one, number 16, and then we're going to go on to exploring instantaneous rates of change using graphs. Okay, so number 16 says a spherical balloon is being inflated. Estimate the rate of change in its surface area with respect to the radius when the radius is 20. So what I'm going to do is I'm going to use this formula. I'm going to take the area when the radius is 20.999. So in other words, I'm going to take area when it is 20 for pi 20 squared. Right? Then I'm going to take the area of 20 plus h, where my h is 0.001. I'll do 3 zeros. I'm going to take my area minus h. And then I'm going to compare these two and these two. Now for calculations, it's going to be easier if I use decimals. So I'm going to use decimals. And it's interesting to note that this is the area of the balloon, not the volume. So you notice the area of the balloon is very much like a circle growing, except instead of pi r squared, it's 4 pi r squared. We'll get into more of that later. And we're only interested when r is bigger or equal to 0. So there we go. So if I take a20, I get a, I got to do a based on r. There we go. If I get a20, I get this. Which means that when a20, the area of the balloon is this. And when I get a20.001, the area of the balloon is this. Slightly bigger. Which makes sense because the radius is slightly bigger. You notice it's 5.9 instead of 5.4. And then when I take the area of the radius, when it's slightly smaller, 19.999. It's that. Now I want you to note something that is easy to mess up. When you're taking slope of something, you need to take the point just after it. Let's see if I can do that. There we go. This one's slightly smaller than this one. See, it's 4.9 instead of 5.4. Now, I want to make a point here before I move on. When you're using h, and you're using h just before it, in other words, this is h minus 1, you're interested in this point here, and you're taking a point just before it, the important thing is to take that point, which is a20, minus the a20 minus h. And and it's important to have the minus h over here if you're going to divide it by 0.001 or whatever your h is. If you happen to mix these up and put this one first, you're actually taking the slope in this direction, which means you'd have to put a minus in front of it. So it's very important to understand what slope, when you're taking slope, you're taking the point after this point, and since this point is 20.001, you can divide it by the difference, and the difference is going to be positive, because when you're going up here, you're increasing your delta x by 0.001. If you were to mix up these values, if you're doing a2 minus h minus this, you're actually not going in this direction anymore. You're taking a slope that way, and you're going to get a reverse sign issue. You're going to get a reverse sign issue. So it's very important that you understand when to use minus h and when to use plus h. So the minus h is a point just before the point you're interested in. Therefore, you must do the point you're interested in minus the a20 minus h to keep this part positive. If you screw it up, you better learn to turn this negative. But you never really want to do that. You always want to keep this h down here positive h. So make sure you have these in the right order. Reverse this spot over here, which is plus h, is going to be further then along the graph than this one, because it's moving that way. It's moving plus h along the x-axis, which means for that formula you have to do area of 20 plus h minus area of 20, because while this is the point I'm interested in, this point is slightly after it with the plus h. And then I divide by h. And you'll see that in your textbook, and it can be confusing. So if you're looking at a point that's just before the point of interest, you have to put the point of interest minus that number. If you're looking at a point that's just after the point of interest, you have to put that one first minus that one if you're going to leave the h as a positive h. And generally speaking, mathematically, this is the sound method to do it. So keep that in mind. Where you put the plus h and where you put the minus h makes a difference in whether the slope, the rate of change, is going to come out minus and positive. If you mix that up, you're going to get the reverse answer that you need, and that comes from your knowledge of how to take slope. But in any case, let's go back and look at the 2 points we're trying to do here. We're trying to measure the rate of change of 20 to 20.001, which is 20 plus h. And we're trying to measure the rate of change of 19.9999 to 20, which is 20 minus h. So the first one, if this is the first one and this is the second one, the first one's formula is going to be rate of change is equal to area of 20 plus h minus area of 20, all divided by h. And in this case, my h is whatever I added to both and subtracted from both. My h is this, 0.0001, 3 zeros. My second one, my rate of change, is going to be area of 20 minus my area of 20 minus h, and that's because the area of 20 is after area 20 minus h on the graph, divided by h. Don't mix that up. It's really important. So this is the case when the point is after the point of interest, and this is the case when the point is before the point of interest. And it's in your book. I might have glossed over it though. So that means number 1 is equal, the area rate of change of number 1 is equal to, this is 20 plus h, that minus this. Okay, minus. See if I can get it perfectly. There we go. Minus that, divided by h. And my h for this one is 0.001. 3 zeros because that's what I took in the 20.0001. So if you take your calculator, you would actually use your exact numbers, but I'll just use the numbers I wrote down. They're going to be pretty close, so if you get 2 different numbers, go reevaluate. $2,574, and click your equals, because if you hit division, your second number is going to be divided by 0.0001 before it's subtracted. In the top part of this, the numerator should be in brackets to emphasize that. It's because I want to do the subtraction before I do the division. And I get a rate of change of this. Okay. So that means my first one, my rate of change is this. So it's changing that many meters squared, or whatever, if it's centimeters squared, per every increase of radius. And then the second one is going to be, if I move this one over, the second rate of change is equal to this formula here. So I've got to take my original dot and subtract this, and again divide it by the same h. This way I don't have to change the signs of my h if I do it properly. So looking at that, let me see if I can do it this way this time. 5.5026.54824574 minus 5026.497980, and I just need a bit more there, 8039. And then I'm going to hit enter, and then I'm going to divide that by my h and hit enter. Now if your numbers are way off here, you did a calculation error, and you could see that this one's approaching. The set for this rate of change is, oh, by the way, this is the first rate of change, and the second rate of change is equal to this. Oh yeah, it's right there. What number do you think it's trying to approach? Well, it looks to me that it's trying to approach 500. So if I was going to now let Desmos do it, I can now just punch in my rate of change formula right here and say my rate of change, and just call it can't call it R, let's just call it change, is going to be A of 20 plus H minus my A of 20, and all of it divided by H. But that doesn't help me until I set H, does it? So on this next line, I should, I'm just going to call this let's just call it my M, my rate of change. This next line, I have to set my H 1. So we can see I got the number I got with my 20. Now let's just add a few more zeros to this. Okay, you can see that it's not approaching 500 at all. It's approaching pretty much, oh no, there it goes. Let's see. Oh, can't handle that one. So it's after a certain number of decimals, it can't handle it. Okay, interestingly, that one is approaching 500. So I would probably take a guess and say it's 500. Now, if I use my calculus method, I can super cheat and just take the derivative of this, which is 2 times pi times r, and then I can just punch in the 20. It's not going to approach 500 because pi is going to make it slightly off. So my actual derivative, using derivative, is 8 times 2 times pi, well, times 20 times pi. Let's take 3.14159 and hit enter. And I did something wrong there. It's 4. It's 8. Sorry, 8 pi. So it's 8 times 20 times 3.14159. 502. So it is actually approaching closer to 502.65. And you can see that this one is visually the same, but you just take the average of those two and you see it comes to 0.75. Now, the smaller I make h, the more accurate you're going to get to it. Since it's an estimate, it's a pretty good estimate. Okay, let's move on to the next chapter. The next chapter is saying we're going to look at some graphs and try to come up with instantaneous rate of change based on the graph. And here they're taking some points that get closer and closer to each other, much the way I've been using Desmos. And then they're looking at what I've already explained to you, a tangent line. Tangent line is a line you're drawing that you're trying to get 90 degrees to the, you're trying to make it parallel to the slope, but it's 90 degrees to the hill of the graph. So for instance, if I'm drawing it and I do a curve like this, the tangent line is different wherever I place it. So the tangent line for a spot right here, for instance, let's say just there, is sort of 90 degrees to that hill. So it's like that. Whereas the tangent line right here is more like this. And even then I have to move it. like, and still even then it's tilted a bit. It's like that. And you can see the tangent line is kind of guesswork, but once you get a tangent line drawn, you can then draw a triangle, and this is the run, and this is the rise, and essentially you can figure out the slope. Now obviously in some spots, the slope's going to be negative. The tangent line here is like that. The tangent line here is almost straight up. Tangent on the top of the hill is pretty much a horizontal line. So for graphs that are curvy, you're going to get different rates of change depending where you are. And the goal we're aiming for is trying to come up with a method that gets us a consistent answer. All right, let's keep going, and then it just summarizes it. So a secant line is when you're using average rate of change between 2 points, and a tangent line is a guess, sort of, you're trying to come up with a line that will show you instantaneous rate of change. And you can usually draw those tangent lines in that tool I attached last time, in which I had this, I think I attached in one of the things. It was slope, intercept form, standard. Oh, I don't think I've signed in yet. Hang on. It was secant and tangent. So here you can see that I'm using this thing, I'm drawing a secant line, and here's the purple line there, and I think the purple line, let's see, yeah, the purple line right here is the slope of that purple line. Notice as I get my secant line closer and closer to that point, especially if I zoom in, it's going to approach the actual slope of the tangent. See, we're almost there. This is the slope of the other line, the secant line. I'm going to get it right close, and if I zoom in really much more, you can get it even closer. So that's really close. That red and that green dot are the secant line, and it's really close, and you can see it's almost matching it. But if I zoom in, it still will not match it perfectly, and I can still bring it closer. And that's the point we're trying to get with average rate of change. We're trying to get as close as possible. There's pretty close there. But with a tangent line, this one, where we end up having to sort of guess with it. Now this one's doing it for me because it's calculating the tangent for me, but you can see up top, that should be pretty flat. And sure enough, the slope is almost 0. And then when we're on a steep curve, the slope's going to be a bigger number. Okay? And like that. And you can hit play on this thing. It'll move the tangent line. Here's the tangent dot, and I can go right out like that. And you can see it's riding up and down. Now, if I stop it at any point, so you can see all those will be positive. Way down there. You see how steep this slope is? It's 6. Now I'm going to hit play, and I'm going to stop it on the other side. That's heading down now, and the slope is -3. And as I get steeper and steeper down this slope, it gets very steep. -7 where it is now. And it'll get steeper and steeper as I get down there. There at -9. So the point is a tangent line is great if you know how to do the formula, but it's very hard visually to do. Okay, graph each of the following. On your sketch, draw a series of secant lines that you could do to estimate the slope when the tangent is x to 2. Record the slopes of these secant lines. Use the slope to estimate the slope of the tangent line when it's 2. So the first one, 3x squared minus 5x plus 1. So there, we're looking at a parabola. It's the black line, and there's my green line. Will it draw a purple line for me? Yeah, there's my red line. So those will help me draw a secant. So my first thing is I can just put my purple line at where we're looking for. There we go, which is x is 2. So let's see if I can just move it down to when x is 2. So we can see that the slope of this line, which is here, is 7. Now if I pull down some, if I pull down my other lines to use them, so I gotta find the other one, which is way over there. See if I can just bring it down normally. See if I can just make it 2 and get it in the right, and we'll put it at 3. And we'll put this one at 1. See if it gets it. Yep. So I can see that if I draw a secant line and take the slope of that, it's also 7 where it is. But if I move this purple a little over there, look at that, it's 3.61. It's not quite accurate. But as I said, as I get closer and closer to this dot, I'm going to start getting very close to the actual slope. Now, but how would you do that mathematically? Okay, you take your formula and you would figure out several points to the right and left of the one you're interested in. So the first step I would do is figure out your f of 2, which is the point of interest. And you get 3 times 4, 12, minus 10, 2, plus 3 is 3. So right away you can see that the point is 2 comma 3. And if you were to take the graph, let's say you have the graph drawn out, you could do the graph. And let's just get rid of some of that stuff. Let's put these on the other line and just get rid of them. Okay, so if you were to zoom in on 2, which is right there, okay, and you were to take a picture, and actually I'm going to try to highlight the 2 spot perfectly. Can't quite do it. Well, if I zoom in, I can do it. It doesn't matter. It's roughly there. And you take a picture. And then you put it on your graph. And then you try to draw a tangent there of that image. So if I try to draw a tangent line in red, let's say, you can see it's pretty much on top of something like that. Even then it's not quite. It's more like that. Not quite. You can see it's pretty tough to read the right tangent line. Something close to that. Great. Now from that point, if you had a nice clean line, you could form a triangle. So let's say 1.5 is right there. And we don't have to use lines after if we don't want, and we can use 2 there. Now, we know the distance between this point, which is roughly, actually I didn't even get the 1.5. The 1.5 is more like down here. Okay. We can roughly say the delta x of that now, which is how far did it travel along the x-axis from this point to this point? Well, 0.5. So the delta x is 0.5. Positive. It moved to the right, 0.5. And how high is this? It went up 1, 2, 3, and whatever that is, 3.2 it looks like. So the delta y is 3.2. So if I take my slope of that triangle, I get 3.2 divided by 0.5, which is roughly 6.4. So you can see the inaccuracy, mostly because that tangent's probably not as steep as it should be. The tangent should probably be more like that steep. I can only roughly get 6.4, and I already know that the actual answer is 6 times 2 is 12 minus 5. The actual answer is 7. So even graphically, I didn't quite get what I wanted. Then algebraically, you could take an h of 1 and an h of 0.1 and an h of 0.01 and an h of 0.001, and you can come up with the right equation for it. Here, let's see if I can do it over here. So if I have f of x is equal to 3x squared minus 5x plus 2, was it? Plus 1. And I make my h equal to 0.00001, and I take an f of x, so I'm interested in 2, and I do a value just after it, and I subtract my f of 2, and then divide it by h, I'm going to get 7.003. If I make my h less accurate, if I take out some of those zeros, like 0.1, I'm going to get 6.3. So you can see that you can just develop a formula that gives you some good values as h gets bigger and as h gets smaller. It should never go negative, though. It should be from 0 to 1 in steps of 0.001. And if I hit the play on this, you can see my values get way out of whack as h gets big and gets way more accurate as h gets really small. See? Approaching 7. And this just essentially lets you take 2 points beside my interest point. I can even do it like 2 plus h and 2 minus h. And that's 2 points on either side of f of 2. That's h distance away. And in that case, then I'd have to get even more accurate with my h because it's 2 times h distances away. Oh, and I'd have to take my h and divide it by 2 because I'm taking 2 distances away. Or multiply, multiply by 2, because I'm taking 2 h distances away from my dot, which is a reinvention of the same strategy. It's just putting the dots on either side h distance away, which means they're 2h apart. But you should stick with what the textbook gives you. You should just stick with, you're going to do one with h on the right side, and then you're going to do one with h on the left side, which is minus h. And you're just going to adjust your h. And you can see, let's say if my make my h equal to 1, you can see that I get no information out of it. I'm going to make my h a little bit smaller. It's not even close with that. It's not even close with that. It's getting sort of close with 0.01, 0.001, and you can see the smaller I make my h, the more accurate I get to the actual value of 7. Now you can do this with each of these graphs, and so I'm not going to do it. And so I'll do it with the next one. It's a growth curve raised by 1. And it's a growth curve with base 3, I believe. Yeah, 3 to the x plus 1. And then when we're interested in f of 2 here, we can find out that f of 2 is 10. So it's way up there. There's f of 2 right there. So if I was to take a screenshot of that, and then try to guesstimate graphically what I'm dealing with, I would just take an image of it, and I'm going to try to draw a tangent line in black. Looks like it's something like that. And you know, there's just not enough information in there. And I also need to know the units, which I didn't mark down properly. So I would have to see, okay, well that helps to know that's 1.0434, 0. So I'll pretend that's a point on the line. but that's on the over here. That's right here at this dot. It would help to know what this one is. And you can see that coming up with tangent lines, especially when you don't know the unit, is very difficult. Let's just put, I don't want that one anymore. Let's just put that back on the graph. It's 2,5. Let's put 2,10 on the graph. There we go. And that way we'll get some units. And even then it would help to know 15. Yeah, there's 15. So then when I go and try to graphically do this, and I'm trying to draw a line, you can see how hard it is to come up with a good tangent line. Probably something like that. Even that's not right. Close. Probably something like that. And we can see we have a nice dot right here at 1, 0. And we have a nice, where's our next dot? That's not bad. That dot there is 2.5, 15, which means if I draw a straight triangle down like that, and a straight triangle across like that, my delta x is 2.5 minus 1, which is 1.5, and my delta y is 15 minus 0, which is 15. Then my 15 divided 1.5 is the slope of my tangent. And if we take our calculator, we come up with a rough tangent idea of 10. So we know that the slope, the rate of change at that spot, is also about 10, which is 1.15 divided by 1.5. Now let's let Desmos do it. And we're going to take our f of 2 here and our f of 2, and we're going to use an h of 0.1, and we're going to let it calculate for us. And we do and see that it is indeed close to 9.8. Let's make our h really small. Yeah, so that tangent line estimate wasn't too bad. And if I take my actual slope, actually I can't really, because the derivative of 3 to the power of x takes some logs to do it. You can see that it's not too bad. Now I can actually do f prime of 2, and it'll tell me. Yeah, there we go. There's the actual slope. So you can see graphically we didn't do too bad. We had a slope of 10, but it's not quite accurate. And the actual slope is 9.875, and you can see our h's got much closer to the actual slope. So graphically there's always going to be some error. Then they want you to do it with a root, x plus 2. And the nice thing about this thing is no matter what I put into the formula, it's able to calculate my h's for me. So here, when s is 2, we can see that the point is 2. So it's 2, 2, right there. So if I was to zoom in like that, keep my points visually there, take a print, put it on this screen, and try to draw a black tangent line. It's pretty hard. It's something like, yes, I didn't quite get it there. I have to move this one up a bit. No, almost. It's something like that. Still not quite. Something like that. That's pretty close. And then if I can just extend it a bit. There we go. Good. That's close. And then I can make a triangle here. That's -1 here where it intercepts. So I could make a, where's a good triangle? Let's go way out here. Pretty close there. So I mean it's there to there and there to there. And I can see my delta x is huge because that's 2, 4, 6. So it's 6 here and almost -1. Let's go even further and make it accurate. minus 1.4. So the difference here is 7.4. And then the height goes from 1 to almost 3. Let's call it 3 minus 1. Let's call it 2.9 minus 1. So my delta y is this, which means my slope is going to be 1.9, my delta y, divided by 7.4. Let's see what we come up with there. So we get a very small slope, and it's equal to that. And it's repeating. So 2, 5, 6, 7, 5, 6, 7, 5, 6, 7, 5. So the 6, 7, 5 is repeating. And when you have three numbers repeating, you just put a solid line across all three. There. Now let's see what the actual slope is. We're going to take right here. It's done my h for me already, and we'll just take a normal h. And you get 0.5000. Not bad. So you can see visually we had 2.6256. The actual one's closer to 0.500. And when I take the actual f prime, yeah, it's 0.25. But visually we came pretty close to an estimate by drawing. And then they want you to do the last one in the same way. And the last one is right here. It is a straight line. There's no need. The slope of this straight line is going to be 2 no matter where I take it. 2x plus 7. And the f of 2 is at 11, so 2 comma 11. So it's way up here. And you can see when I take a visual and I draw the slope from, let's say, this point up to this point, because the slope is also going to happen to be, the tangents also happen to be right on this line, you can see that it's already revealed. So it's going up 1, 2, 3, 4, and over 2. 4 over 2 is indeed the slope of my tangent line, which is also the slope of this line. That's because the tangent line is on this line. And you can see it all here as well. The f of 2 with h small came out as 2. And if I do f prime of 2, which is a way of saying what is the exact slope at 2, it gives me 2. Verify your estimates by drawing the tangent line when x is 2 on your graphic calculator. So that's just essentially use your Desmos. Graphic calculators are pretty old-fashioned. And I don't know if I would do it. For each of the following sets of function, estimate the slopes of the tangents at the given values of x. So they want to take a downward-facing parabola when x is equal to 3. When sine x, they want at 90. Well, I can tell you what that is. At sine x, the peak at 90 is the top, so the slope's going to be 0. Therefore, this tangent of the slope is going to be 0. The tangent's going to look like this. This is an upward-facing parabola when x is minus 2. And then this is just a vertical line. So the slope is uncalculable on vertical lines. It does not exist. Therefore, the tangent of a vertical line does not exist, and so you cannot ever come up with that for vertical lines. But you can again take your calculator and minus x squared plus 6x plus 4. And I urge you to do this on your own with Desmos, because you'll get minus 4 actually, because you'll get so much more information. So that first one they want to do when x is 3. So we'll figure out what y is when x is 3, and it's 5. So we're looking at the point 3, comma 5. And I'll just do that, and there we go, downward force. Okay, so that's at the vertex. Well, I can tell you that the line, the tangent of that line is going to be this. And the slope of that line, because there is no rise, so 0 divided by whatever run I use, is going to come out as 0. 0 divided by 7, 0 divided by 9, doesn't matter. The slope of a horizontal line is 0. So they're just being tricksters. Same with the next one. They want to know when it's 90 degrees for sine x. And just make sure your thing is in degrees and not radians. And then it gets really flat like this because the x-axis isn't properly displayed. There we go. And go from -1 to 1. There we go. And then they want this point, f of 90 degrees. Well, that's right there at 1. So it's 90, comma 1. It's right here. And again, the line for that is the tangent line would look like this, and the slope is 0. So they're just having games with us. Then finally, x squared plus 4x plus 11 when x is -2. I think that was it. When x is -2, so we'll find out what f of -2 is. And we'll put it on the graph. It's 7. Okay. We'll get rid of this. And we'll see where this line is. There it is. And look at that. They've given us the vertex again, which means the tangent is going to be right here, and the slope of the horizontal line is 0. So they're just goofing around and making you figure it out. And they're saying, what do all these slopes of each set of functions have in common? These are a horizontal line. These are all vertical lines. You can never, well, we'll have to see, but I'm going to guess they're all vertical lines. Sine x when x is 60. Okay, that's on the upward side. It's going to be something like this. So let's do this one first. 3x squared plus 2x minus 1 when x is 2. And when x is 2, we can see that that is 2 comma 15. And it's on the upward slope of that graph. So if I'm going to draw it, it's quite steep, but I'm just going to use this instead, and we can see it's approaching 14. But again, if you're going to draw, you try to draw a vertical line, 14x plus or minus, what is it, 15, I think? Yeah, there we go. If you're going to draw a tangent line, it would look something like that, and then you'd use your triangles to try to get a good idea of what the slope of that line is. But just take note, it's roughly 14. What about 2 to the power of x plus 3? 2 to the power of x plus 3. And you can see that that point, I'm going to get rid of that, is 7. Is over there. And the slope of that one's 2.77 roughly, but if I was going to draw it, a tangent line, it would look roughly like that plus 7, no, minus 7 I think. No. Plus 1.1, 2, no, 1.5, somewhere around there. And you would take a delta x and a delta y. You'd essentially draw a line from here and here. And you'd take that triangle and find its rise over its run and determine what the slope of that tangent is. And then the next one is 5x plus 4. Well, that's a straight line. When x is 3, doesn't matter where x is on a straight line. That's going to be the slope, 5. And as I said, sine x 60 is on the way up. When x is f of x is sine x, f of 60 minus 60. The slope is roughly 0.08. Let's see if we can find what we're looking for, f of 60. Did it remember to keep my... Yeah, it did, but it reverted it back. 0 to 360. And minus 1 to 1. we go. And where's the point we're talking about? It's 60, comma, 0.8660254. It's that one. And you can see from my h that the slope's really tiny. Interesting, it shouldn't be. It should be quite significant. It should be about, it shouldn't be that small. No, it is. Okay. So you'd be looking at a line like this. A tangent line you would draw like this. Plus 3, 2, 1, 0.2, 0.3, 0.4, 0.35, something like that. And then you would take the slope of that tangent line. You're essentially trying to draw tangent lines and just do a triangle right on it. So that you can take the slope of that blue line. That's what tangent lines are. You're trying to draw them 90 degrees to the dot that you're interested in. They want you to keep doing this. Again, I don't think it's worth it. That's a line, so it's -2. That's a line, so it's -3. It doesn't matter where the point is. The slopes of the tangents will be the same as the lines. And that's a parabola. And when it's -1, it's 3. -2, -1, it's 0, comma 0, and it's lowered by 1. So it's probably over here on that parabola. I don't know if those are worth doing. Following tables gives the temperatures of an oven as it heats up. Graph the data. Okay, you know what I'm going to do this time? Yeah, you should definitely learn how to graph this. But I'm going to see if this will do it for me. I'm going to create a table. And I'm just going to put in 0, 70. And for y's, I can see I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then for the temperatures, I got 7, 70, 125, 1, 125, 17, 210, 250. It should be consistently heating up. 280 looks like it's going up by close to 30 each time. 360. There's going to be a couple dots off. 380, 400, 415, slowing down. 430, 440. Oh, because it's heating up to a specific temperature. So as it gets close to that temperature, it's slowing down. So my y's from 70 to 445, and my x is from 0 to 14. And now I'll enlarge it. There we go. And you can see it's slowing down as it's getting up there. And then they want you to draw a curve that best fits the tangent line of x equals 5. Well, x equals 5 is right here. Okay. So if I was to take a picture of that and do it old school, it would be for this. And I would probably do it something like that. Close? No, it's a little off. Yeah, it's close there. And then I would just look at it. I would say, okay, from here, roughly, where's a good point? That's pretty much halfway. And then I would take it up. Where's a good ending point? Probably to there. Good. So I can see that this goes from 0 on the delta y 0 all the way to this point, which is 6, 7, 8, 9, 0 to 9. So my delta y is 9. Sorry, delta x. And my delta y goes to about 150 here, all the way up to 400. So my delta y is 250. which means my whole slope of that graph is 250 divided by 9 at that particular moment at this dot. 250 divided by 9. So the slope of that graph is roughly 250 divided by 9. 27.7. So the slope, or the rate of change, instantaneous rate of change at x is equal to 5 is 27.777. Okay, let's see if that's true. So the nice thing about Desmos is actually capable of trying to come up with a curve. If you use this symbol, and now what does that look like? It looks like either decay curve flipped up, or growth curve, decay curve flipped upside down, or we can do a square root curve. And we can just say x1. And then it's going to give us roughly the graph that fits. And let's see. I think I have to do like plus C in there. No, might have to do this. Oh, right there. The first start is for sure. It starts at plus 70. Okay. Starts there. So I would be, oh, I put the plus 70 at the wrong spot. Plus 70. Okay, so that's not right. And let's see if I can do it. Y is equal to square root of x plus 70. It's not even close, so we have to, we have to stretch it. And sorry, usually Desmos is good at that. So I think what I had to do is put an A value here, and then it would come up with an A for me at 99. So y is equal to 99.8 square root x plus 70. Not bad. It's kind of doing a line that best fits. I might also want to do a negative decay curve of x plus 70. Yeah, and then multiply it by 100. Oh, sorry, negative growth curve. No, that doesn't work. I think I'd have to keep the 100 here and put the negative 2 to the power of x, and I'd have to put the negative in front of x. And y? Yeah, something like that. Let's see how complicated that one gets. Yeah, no, that definitely doesn't fit. So really we're looking at a square root graph that best fits, and even then it can't really do it very well. It definitely doesn't stretch out that much. Yep. 88, 90, 5, 6. Yeah, actually 99 is pretty close. Yeah. So even then, you can't really get a good idea of what's going on. You could take the calculations from either side of it. So you could find the rate of change from here, which is 30, and the rate of change from here, which is 30. And what did we come up with? 27 point there. So the slope between these points is 30 and the slope between these points. How did I do that? Because the delta x here is 1 between those and the delta y is 30. So 30 over 1 is going to be 30 between these 2 points. And then between these 2 points, the delta x is 1 and the delta y is 30 again. So that means the slope here and slope here is 30 on either side. So it's pretty close. It's somewhere around 30. You could also do the average rate of change for the whole thing, or take a couple more averages right around 5. But that's pretty good estimation that we've done. Yeah, estimate the instantaneous rate of change exactly 5 minutes using a centered. Yeah, so that's taking on either side. That's taking from 4 to 6. So the change is 250 to 310, which is 60, and it went up 2x values, so 60 divided by 2, 30 still. In the first 2 sections, and then compare your answers to part C and D. Yeah, we did. In the first 2 sections of the chapter, you calculate the slope of successive secant lines to estimate the slope of the tangent, and you calculate the average rate of change. How are these 2 calculations similar and different? And you I'm not sure what they're asking, but the closer your dots get to the actual dot on either side of it, the more accurate your instantaneous rate of change guess is. On graph paper, sketch this parabola. Draw a secant line that passes through those 2 points. Estimate the location of the point of tangent and the graph of x. Same slope as the secant line that you just came up with. Okay, so that's just between points 1 and 2. It'll probably be exactly between those 2, by the way. So we'll just go back up, get rid of this, and we're going to do f of x is equal to x squared. And then we're going to find f of 1. Then we're going to find f of 2. And we're going to hit that. And we're going to put the dot 1, 1. We're going to label it. Or if you want 1, f of 1, we're going to label it. We're going to put the dot 2, f of 2. We're going to label it. There, we can get rid of these. And we can see those are the 2 dots. I can draw a line. What's the slope between those? 4 minus 1, 3. And 2 minus 1, 2. So 3 over 2. So I can draw a line. Y is equal to 3. X. And then I just do x minus, I think it's x minus 2. And y in brackets minus 4. Close brackets. There we go. It now has a line that joins those 2. And let's make it a different color. Let's make it red. And there's the secant line. And I can see quite obviously that the slope between those secant lines is that. Now if I'm going to guess, I'm going to guess that the line, the dot that has the same tangent is going to be f between those 2, f of 1.5. So I'm going to guess it's this dot, 1.5 comma f of 1.5, the dot that's right in between. And then if I just draw a same line, I do y minus 1.5 is equal to 3, x minus 1.5 to come up with the line that passes through it. Sorry, that's 2.5 for the 2.25 for the y. And then I'm going to have a line that pretty much looks like the tangent. Let me turn off the other one. Pretty close to the tangent. Now, just to make sure I'm right, because the tangent I'm claiming is 3, I'm going to take the f prime of 1.5, which will tell me the exact rate of change. It's 3, and then I'm going to take the f prime. Can't really take the f prime of the other one. Yeah, it's 3. So there we go. The rate of change that matches the tangent slope that matches between 2 and 1 happens to be the point exactly between the 2, which sort of makes sense. I don't know if it always makes sense for a parabola, but it does in this case. And that's it. This chapter's more about using graph and how to draw the lines and figure out slopes from a line of a tangent. Visually, tangent lines are very hard to draw.